Section 1.3, Functions and their Graphs. This video will help you use mathematical language to describe increasing, decreasing, and constant functions, understand the extreme value theorem, and identify characteristics of even and odd functions. All right, let's take a look at increasing functions. A function is increasing on an interval if f of x sub 1 is less than f of x sub 2 when x sub 1 is less than x sub 2 for all x1 and x2 in this interval. Okay, it's a lot of information there. Let's kind of go through and dissect it. Really, all we're saying is an increasing function is, take a look here, here's an increasing function. We'd say, if we were going to say this in real simple terms here, this function is increasing, it's going up as we go from left to right. Right? But we want to make sure in mathematics we're describing the situation precisely and using mathematical language, because that language is very precise. So let's see what this means. First of all, I think if we kind of work backwards here, we're looking at an interval. So we're not looking at this function entirely here. We're only going to look at this function on some interval, which means I'm going to kind of cut this thing off. So let's see here, if I started about here, let's say that's the beginning of my interval. Here's the end of my interval. So I'm only going to consider this function from my x coordinates over here. Looks like maybe -5 or 6, maybe all the way up to +8. That's the interval that I'm looking at here. So x1 and x sub 2 are two x coordinates on this interval. So I'm going to have an x coordinate here somewhere and another one somewhere else in here. And we know this, that x sub 1 is less than x sub 2 anywhere on this interval. So now that we've got that established, now let's go ahead and look at the function values. So you now remember f of x sub 1 means I'm going to evaluate the function at this coordinate. So in this case, right down here, I would say, all right, that's f of, and again, maybe let's say that's maybe -6. And it looks like when I evaluated this point here, it looks like maybe we're at -4 or 5, something like that. So that's the function value of that coordinate x sub 1. And if we look at the function value of coordinate x sub 2 here, the f of x value is somewhere up here, maybe +7 or +8, something like that. So that's what we mean by this notation. So f of x sub 1 now, when we evaluate the function at this location, is less than f of x sub 2. And so we're using this language now to talk about anywhere on the interval. So anytime that my first x coordinate here is smaller than my second, then we know the function value at that first coordinate is going to be smaller than the function value at the second. And so that's how we describe that using precise mathematical language. Okay, we've kind of talked through a increasing function here now. What I'd like you to do now is pause your video player, and using the same sort of language here now, I would like you to finish this decreasing function definition. So go ahead and pause your video player now and use some of the things that we use on the increasing function, and go ahead and write out your decreasing function. And when you get done writing it out, go ahead and hit play to see how you did. All right, let's take a look and see how you did. So here's the definition I came up with. I said a function is decreasing on an interval if the function evaluated at this first x coordinate is greater now than the function evaluated at the second x coordinate when the first x coordinate is less than the second. So as we move and get to larger x values here along the x-axis here, the f of x, or the function values, now are decreasing, meaning that this first one is going to be larger than one if we evaluated it down here a little further down the function, or a little further more to the right with an x coordinate of the function. So hopefully you came up with a decreasing function that looked like that. Okay, so hopefully you found a little bit of success writing your first definition there about a decreasing function. Now what I would like us to do is go ahead here and write a definition now for a constant function using very similar language. It's not going to be exact, but now we're talking about a constant function. And a constant function, I've got us a nice little picture down here. A constant function doesn't change. So as my x coordinates change, the f of x values remain the same. And so that's kind of the layman's terms for it. We want to go ahead now and use some of our precise mathematical definitions to describe that situation. So go ahead now and pause your video player again and finish this constant function definition. All right, let's take a look at your definition here and see how you did. So here's what I wrote for my constant function definition. A function is constant on an interval if f of x sub 1 is equal to f of x sub 2 for all x1 and x2 in the interval. Now notice I didn't have any less than or greater than symbols here because I don't think they come into play. You know, basically for any x coordinate that I pick on a certain interval here, let's say just for an example here, let's say we went between those two places, x coordinates, to talk about my interval now. For any x coordinate on this interval, I'm always getting this same function value there. Now it wouldn't be wrong if you wrote this for all x sub 1 less than x sub 2. That is still true. It's not a false definition, but the fact that one is less than the other really has nothing or comes into no play here in terms of our definition. It really just works for any x coordinate here, regardless of whether one's larger or smaller than the next. But if you did write this, which students typically would write that, it's not wrong, but it's a little misleading because it says to the reader that somehow it matters between these two x coordinates and the relative size of those x coordinates, when it really doesn't. All right, let's take a look at a couple other definitions here. A relative maximum. We'll read through this and then we'll kind of talk through it to make sure you get it. So relative maximum. F of a is a relative local maximum of a function f if f evaluated at this point a is larger than any of the other f of x values. And I know for any of the other because I'm saying here afterwards for all x and a, an element of this open interval. So let's take a look here and see exactly what we're talking about. So we've got some sort of function here, and I'll just sketch something out. And, you know, we've looked at some right now that are kind of not very exciting functions, but we could look at functions that have more curves and twists here. So in terms of this definition, a relative maximum, based on the picture that I drew here, a relative maximum could occur here and here. Those could both be relative maximums because they're maximum values relative to the other points around them. So maximum values relative to the other points around them. And so that's why relative to these other points around them, we're not looking at the whole function here as a whole. We're only looking at a part of it. And the way we know that is because we're just looking at an open interval. So we're just looking at some interval here. And again, let me just make some interval here up. Let's say we were starting at that x coordinate and ending at this x coordinate here, and that's the interval that I'm looking at. Just over that little local interval, we would say this point is a relative maximum, and we could say right here too, if we looked at this, you know, we could look at this open interval there, and in that open interval there, we could say that point there was a relative or a local maximum. Now again, interchanging the words relative or local maximum, you hear both of those values. Now, neither of these 2 points would be an absolute maximum because we can see overall that this function is still continuing upward, and there's going to be some greater values to this function up here somewhere. But locally, we could say each of those two are a maximum. So let's go back now that we understand that idea, and let's look at this relative maximum definition again. So f of a at our point A here is a relative or local maximum if the function evaluated at this point A is greater than all the function evaluated all these other x coordinates around it. And we know it's just around it because it says for all x and a, an element of our open interval. And again, just this smaller open interval we're looking at here. Okay? Why don't you go ahead now and let's pause your video player, and why don't you finish the relative minimum definition, again using this language, this mathematical language we've been kind of demonstrating here. Okay, let's take a look at your definition here for relative minimum. And it really, hopefully, was a pretty easy task for you here, because all we really had to do was take this greater than sign and turn it into a less than sign, because now we're talking about just a local or relative minimum point. for all x and a an element of this open interval. And I hadn't talked about this before, but let's look at this word real closely here. An element of, all that means is these are x coordinates, an x coordinate and an a coordinate that's on this open interval. So our a coordinate here actually, is just some x coordinate, a specified x coordinate here, a specific one, but it's still just an x coordinate on our interval. And if we were looking at our graph up here, we'd be talking about kind of this area here for a local minimum, and again we'll look at some open interval around that local minimum there. And all an element means is that these x coordinates and this a coordinate are part or inside and contained inside of this open interval. Okay, let's take a look now at an absolute maximum. And an absolute maximum is really the same idea, except now instead of looking at a local open interval, kind of looking at the points around an open interval, now we're considering the whole function. And so f of a is an absolute minimum or an absolute maximum if the function f of a is less than f of x for all x, an element of the domain. And again, a is part of the domain here, but it's a specific point. And the function evaluated at that point is either the absolute maximum or the absolute minimum. The definitions are really almost the same except for the word maximum or minimum. All right, let's take a look at another definition here, the extreme value theorem. If f is a continuous function on a closed interval, ab, then f has an absolute maximum and minimum in at least one location on this closed interval, ab. All right, so anytime we look at a math definition, we kind of got to dive in here a little bit and look at the details now. One thing we'll note right away, we've been talking a lot about open intervals, and now we're talking about a closed interval here. Well, an open interval would just simply mean that we are not including the points A and not including the point B in this interval. And here's how we write an open interval. If I was talking about the open interval AB, I would use parentheses on each side. And that means we would cover all the values between A and B, but we would not include the actual A value nor the B value. We would get as close as we could to these values, but not include them. Now, if I put the brackets around there like I have here, now that means we're also going to include both the A value and the B value. So we're talking about a closed interval here. Let's kind of make a little sketch. So I'll make a little sketch of a graph here. We can talk about this. So let's say the interval is going to start here at A and it's going to end here at B. And we've got some sort of function in there. So I'm going to go ahead and just draw some random function here. Let's say it was going like this. Okay. The extreme value theorem now just talks about exactly that, the extreme points in this graph. So it's telling us that we have an absolute maximum and minimum, but again, just on this closed interval. We're still not talking about these values outside of here. We're only talking about values now on this interval. And based on my graph there, just kind of eyeballing this here, it looks like maybe I'd have an absolute maximum there. And it's hard to say where the absolute minimum would be. We'd have to look very closely at this function. We could say that the absolute minimum was here, but we also could make an argument that maybe the absolute minimum is over there, right at the point A. So we'd have to look very closely at that. But one of these two locations is going to have a lower f of x value, so that would be our absolute minimum on this graph. Okay? So the extreme value theorem says that if I take a function and I cut it off and look only at some closed interval on the function, somewhere on that function I'm going to find an absolute maximum, and somewhere on the function I'm also going to find an absolute minimum at one of those two locations. Now let's see what else we have in this definition, because every word in a math definition makes a difference and is there for a reason. So we've got the closed interval. We talked about that. There, closed interval. We talked about absolute max and min. Let's see this, in at least one location. So that's important. Well, it could have turned out here when we looked at my 2 points that these minimum values are exactly the same. And so if that were the case, these two f of x values here are exactly the same, then we would have an absolute minimum at 2 locations, because we're not talking about it as a single point. We're talking about an absolute minimum as a function value there. So we could have the smallest function value occurring at 2 points. So that's something important to kind of look at and take into consideration. Let's see. There's one other thing we hadn't talked about here either, and that is a continuous function. A continuous function means just that. It kind of has to have a nice, smooth, continuous curve around here. Let me draw you a function that's not continuous. So sometimes we might have a function and some strange things happen, and maybe at this location here we get kind of a weird spot where it's not defined or something funny happens. Sometimes when you have kind of an open spot there where the function isn't defined, you could have a point like that, or a value for the function down here or something like that. But basically, if the function wasn't continuous, this definition would not hold true. So it's important for us to recognize that. This would only work if we have a continuous function. Alright, let's go ahead now and pause your video player here, and I'm asking you just to write down what you know about even and odd functions. You've probably had a little bit of practice with this before, so write down the kinds of things you remember, maybe an example of an even or odd function, or things you notice about them or know about them. If you can't come up with anything, that's okay, but give it a shot, at least to try to do this, and come up with what you can. You know, thinking about it before I show you this will help you remember in the future. Alright, so I've written down for us a kind of a classic even function. And usually when people think about even functions, this is kind of what they think of. This is kind of like our most basic even function. F of x is equal to x squared. And at this point in the class, here are the things that I'd kind of like you to know about even functions. Even functions are symmetric with respect to the y-axis. So that means if they're symmetric, if I kind of take a look here at my y-axis, I get a reflection of one side of the graph to the other. So notice every point over here corresponds to a point over there. So that's typical of every even function. They're symmetric across the y-axis. So if you look at a graph of a function and you notice it has symmetry over the y-axis, it's going to be an even function. All right? And as a result of this, we also kind of get this in there, that if I evaluate this function at a negative x coordinate, I get exactly the same function value of when I evaluate that function at the positive x coordinate. So notice here on my graph, if I look at the point x equals negative 2, and I look at the point x equals positive 2, the function value is the same. It's 4 in both of those locations, and you can see why here when I have this x to the second power. If I evaluate f of negative 2, I'm going to get this. I'm going to get negative 2 squared, which is just going to give me positive 4. And if I evaluate f at positive 2, it's also going to give me positive 4. And that's true for all even functions. The f of negative x is equal to f of positive x. Okay, kind of when we think about our odd functions, we think of f of x is equal to x cubed. And I forgot to mention it before, but you can see now why we call them even and odd functions. Notice it has to do with the powers a lot of times on these functions. So notice we get x cubed, x to an odd power. We end up with this odd function here. And so some things to notice about odd functions. The odd functions now, the symmetry is kind of a little different here. It's not with respect to the y-axis nor the x-axis. It's with respect to the origin. And when we say symmetric with respect to the origin, we're talking about two things. It's either a reflection over the line y equals x, and here's the line y equals x. Notice my x and y coordinates are the same. So this would kind of be a quick sketch of y equals x. So we're either reflecting this graph about the line y equals x, and you can see here, if I reflect the points across y equals x, it's not giving me this graph. So that's not the case. Or it's a reflection across the line y equals negative x. And y is equal to negative x gives us this graph here. And that is the case here. Notice if I reflect this point across the line y equals negative x, I'll get this point here. And you can see, based on that, you know, if I took this point down here, reflected across there, you can see that I'm getting this graph across the line y equals negative x here. The other thing to notice about odd functions is now if I take and evaluate f of a negative x value, I get the opposite function value. So notice if I took, let's take negative 2 and positive 2 again as my x coordinates here. So if I take x f of negative 2, oops, if I take f of negative 2, now I'm taking that negative 2 and I'm cubing it, which will keep it negative. So I get negative 8. If I take f of positive 2, if I take f of positive 2, when I cube positive 2, I get positive 8. So notice my function values here, my function values are exact opposites of one another. And so that's what will happen in odd functions. If I take f of a negative x, I get the opposite of the positive x value in odd functions.